Hello, in this video we will see how to establish sizing scenarios for a mechatronic system using design drivers of all of its components. After analyzing the architecture of the system we have to size, you will have all you need to give the list of the functions it must answer and the components which compose our system. The next step is to establish the working scenarios which could degrade the different components. The scenarios could be expressed as a set of operational points, torque, speed, or mission profiles, quantities which change over time. To illustrate the notion of sizing criteria and sizing scenarios, we will use a flight control actuator, more precisely for spoiler surface as an example. The spoiler reduces the lift of the aircraft in order to start an approach towards the airport or to increase the action of the brakes on the wheels for landing. On the considered aircraft, the actuator will have to position himself on 3 different angles while working against aerodynamic forces. These forces can be either positive, when the surface is fully deployed, or negative, when the surface is fully retracted. No damage must appear in the structure or actuator if jamming happens or when gust action occurs. Here's the architecture of the studied case. It is based on an example, an EMA for the Boeing 787 spoiler, designed and manufactured by Moog. It is composed of mechanical components for effort transmission, such as rod end, rod, housing, for power transmission, ball screw, bearings, gears, and electromechanical components, such as a brushless motor. We're going to determine here the possible reasons of the degradation in the system's components. These degradations can be either fast and come from transient power demands, such as permanent deformation, rupture, or gradual and come from continuous power demands, which often reduce the components and therefore the whole system's lifetime, such as mechanical fatigue. The component can also have imperfections, which can increase the mechanical stresses on itself or over components. For example, the inertia of an electrical motor increases the torque the same motor has to deliver or can destroy mechanical components when a sudden stop occurs. Mechanical components can deteriorate either in a fast way under the effects of a too important transient effort, which can create localized stresses, leading to a permanent deformation or, in the worst case, a rupture, or in a gradual way. Alternated efforts can reduce the component's lifetime by creating micro cracks, which can increase with the number of requests. For example, we must be sure that all of the components can take the maximal effort and determine the situation which generates this maximal effort. Fatigue is often computed for rolling elements using mission profiles that represent repetitive requests. Another source of mechanical degradation comes from the vibratory environment, or shocks, during operating time. For a linear actuator, we need to be sure that the housing or the screw will not be subject to stress due to resonance mode on typical plane frequencies, which is between 5 Hz and 2 kHz. If possible, we will try to eliminate all resonance modes on this frequency range. The mechanical power transmission components, such as worm gears or ball screw systems, have imperfections, such as friction, which reduce their efficiency. These frictions can increase the effort the motor has to transmit and therefore have an impact on the component's choice. It is important to consider the quadrants and the speed in friction or efficiency computation. In our example, we could model our ball screw system with a constant efficiency, except when the speed is 0, in which case we'll increase the friction. A worm gear is generally modeled with a constant efficiency. It is interesting to underline that the friction due to mechanical stops inside the ball screw system depend on the efforts given by the jack. For electrical components, the current and thermal effects can induce magnetic fields, which can demagnetize the magnets. With new magnets, the odds are lower. Or they can induce an excessive magnetic field, which can create a saturation, a TIF level, where stands the winding. In our example, we will consider that the maximum transient torque of the machines will be limited by the sheet's magnetic saturation. The electrical current generates copper losses which heat the motor. Excessive temperature can demagnetize the magnets. The higher is the temperature, the shorter is the lifetime of the copper wire's insulation. The link between lifetime and temperature is given on the following graph and depends on the insulation type. In our study, we will consider that the mean torque will be limited by the winding temperature. A thermal model can be useful in order to ensure us of a proper working. Electrical motors have imperfections such as the energy stored in the rotor inertia. It's the effect of the inertia that we have previously discussed. Losses can also impact the power electronic choice. We have listed the different degradation risks for our application. We're going to list 5 of them here. Under mechanical aspects, you can see a profile which describes expansions and retractions profiles and the associated torque. This profile gives an estimation of the maximum efforts on the entire power chain. Repeated over 12,000 flights, it will help computing lifetimes. Under thermal aspects, we have chosen here an important deflection. That means a high torque which generates important losses in the motor, with an important holding time and high external temperature, which is because we have low altitude in warm country. Vibratory aspects are considered by using vibratory test standards for a given amplitude and frequency. The harmful aspects of inertia is taken into account in a critical case, such as the jamming of the spoiler at full deflection speed, implying maximum stored kinetic energy. And the effort limitation function is represented by a sudden turbulence in the last scenario. To be sure that all of the design criteria are covered, we can use a verification metric listing on one side the global functions of the system and the design criteria of the components, and on the other side the different design scenarios. Each line must be linked to at least one scenario.